Hello, Math 7 students. This is Open Up Resources Unit 2, Lesson 11, Interpreting Graphs of Proportional Relationships. To get started, we read that this here is a graph that represents a proportional relationship. That means I know that this is a proportional relationship because it told me. But we learned some things yesterday. What are some other clues when I look at this graph that tell me that it's a proportional relationship? Again, not just reading what it tells me here, but remembering what we talked about yesterday. Thank you. Let's start with Luke. Yes, we can see that it goes through the origin. That is one of those big clues. It goes through the origin. What is the other characteristic that tells me it's a proportional relationship? Jada. It's a straight line. So those two characteristics, it goes through the origin and it's a straight line. And that word that we use for straight line, CJ? Linear, yep. So it's a straight line that goes through the origin. That tells me it's proportional. Now, through the origin. You guys are given the graph. You need to invent a situation that could be represented by this graph. Think about all the different situations we've looked at throughout the course of this unit. Think even about the ones that we saw in our activity yesterday. We had things like tablespoons of honey and cups of flour, or t-shirts and dollars, or cups of rice and servings of people. And all of those are relationships that could be represented, but I want you to invent your own situation that could be represented by this graph. Once you invent that situation, then you would need to label the axes with the quantities in your situation. So you'd have to actually label it and say this represents blah, 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 and this represents blah, blah, blah. Give the graph a title. I'll explain that one in just a second. But then I also want you to figure out there is a point on the graph. What are its coordinates? I'll highlight that point right now. That point is this one. What are its coordinates and what does it mean for the situation that you invented? Go ahead and work with your groups on this. Take 60 seconds to work with your groups. Online learners, pause the video until you've done those things. Ready, set, go. Okay, we are back. The situation that I am going to invent is the classic way that we started off this whole entire term all those many moons ago, and that is cups of water and teaspoons of drink mix. Does that bring back memories? Yes, that was amazing. Teaspoons of drink mix and cups of water. So for my particular situation where it says invent a situation, I would say something like, let's see, cups of water, that number is 16. So 16, or a recipe calls for, I'll be really detailed. A recipe calls for 16 cups of water. And looks like that number that goes with 16 coming on over here to the side is 12 teaspoons of drink mix. There's my invented situation. Any volunteers who want to share their situations? Great, thank you. Get us started, Sam.
Okay, so I made mine a problem.
Okay, let's hear it.
For every 8 miles, the car uses 6 gallons of gas.
Great, I love it. And I love how you didn't choose the point that was here. You found another point right there. So he said this 8 represents gallons of gas. Is that right? I can't remember.
No,
that was miles. Okay, so this is miles. And this you measured and called it gallons of gas. Great. Notice that I'm using different colors to kind of show each different situation because I'm going to put a couple of different labels up here. Let's go to Trinity. What did you get? So we have to be careful with the 2 cups of rice and 2 cups of water because is that point on the graph? No, that 2 isn't. So let's go cups of rice and cups of water, but let's choose different numbers. What numbers could we use that are already on the graph? Should we use the same ones that Sam did? Or do you want to use the ones from up here? Okay, so we would say cups of water and cups of rice up here. Great. Let's hear from one more student. Thank you, Fitz. Good. Not too bad. That one is a little bit challenging though, because every 3 yards every 3 minutes he's 4 yards closer to home. That number is not on the graph. Over 3 and up 4 is not. Oh, I see. This one right here. Got it. Okay. So X is yards and Y is minutes. That works. Thank you for correcting that. Beautiful. So we've got lots of different options. I'm not going to call on every student who has another idea, but you guys get the idea here. It says label the axes with the quantities in your situation. We did that. So we're going to say C, below, and to the left. Give the graph a title. Now I've kind of used my space up here, but basically what that would mean for my situation is I would just title it and say drink mix and water. For Sam's situation, he might title his miles per gallon or gallons per mile. For Fitz, he might title it something like walking home because his situation dealt with walking home in yards and minutes. So give your graph a title. Your graph title will probably be different than what we've got going on here. And again, it says there is a point on the graph. What are its coordinates? The coordinates are 16, 12. Because we went over 16, remember from our last lesson, we have to learn how to crawl. So we go over first before we can learn how to climb and go up. So the coordinates are 16, 12. What does it represent in your situation? For my situation, that would be 16 cups of water. Because the 16 is here on the x-axis where I'm measuring cups of water. And the 12 is on the y-axis where I'm measuring teaspoons of drink mix. So 16 cups of water, comma, 12 teaspoons of mix. That's what that means. Easy peasy, lemon squeezy. Move on to the next problem. This is Tyler's walk. Tyler was at the amusement park. He walked at a steady pace from the ticket booth to the bumper cars. So imagine what this is like. Close your eyes and envision it if it helps. You're at the amusement park and you're just got through the ticket booth. And you want to walk over to the bumper cars. That's your favorite ride. You're walking at a steady pace. And now, open your eyes. Let's take a look at the rest of the information. The point that's on the graph, see it? It shows his arrival at the bumper cars. And we have the coordinates 40, 50. What do those coordinates tell us about the situation? Talk with your group members. Let's be prepared to write it down. What does this 40, 50 mean as Tyler is walking to the bumper cars? 60 seconds, ready, set, go. Online learners, pause the video. We're back. 40, 50. Let's just start with just the 40. What does this 40 mean? Looking for some brave volunteers. Lots of brave volunteers this time. Chandan, what does the 40 mean? Yeah, he's been walking for 40 seconds. That 40, if we take a look, that 40, remember, deals with our x value. And the x value deals with how far over we're on the graph. And when we're going over, we can see what we're measuring. We're measuring time in seconds. So that 40 tells us 40 seconds. Now let's focus on the 50. What does the 50 right here, what does that tell us? Thank you, all these brave souls. Dakota. How many meters away he is. Again, that's beautiful. Here we have our 50. Oops, that should be Y. If we look at that 50, we're up 50. This here, our Y value, is our second coordinate measuring how far up we are, or in this case, the distance from the ticket booth measured in meters. So that 50 is meters. So let's really understand what that means. 40 seconds, comma 50 meters. What that really means is he walked 50 meters in 40 seconds. He's walking at a steady pace. He's excited to get to the bumper cars. Now, the table, which for me is right below. For you guys, it's on the next page. So go ahead and flip to it and take a look at it. The table representing Tyler's walk shows other values of time and distance. The first thing we need to do is complete the table. So let's take a look here. Let's complete the table. It's almost all the way filled out, but we are missing something right here. We have the tools and the experience necessary to fill out that missing value. So I'm going to set you free to do that in just a second, but let me finish reading the problems that I want you to complete. After we fill in that missing value, it says next, plot the pairs of the values on the grid. The problem for you guys is you have your grid on one side and your table on the next. You have to be flip-flopping back and forth, and that's going to be really annoying, right? So I am going to leave my screen here so that you can see the table, and then all you have to do is just graph your points. Should make it a little bit easier so you're not flipping back and forth. Okay, but that's not all. Let me finish reading all the things you have to do. Answer this question. What does the point 0, 0 mean? How far away from the ticket booth was Tyler after 1 second? Label the point on the graph that shows the information in the coordinates. And what is the constant of proportionality for this relationship between time and distance? What does it tell us about Tyler's walk, and where do we see it in the graph? I want you to answer all of those questions, working with your groups. I'm going to leave my table up so that you can plot those points. The time is now yours. Online learners, pause the video until you've answered these questions and come back to check your answers. Okay, the first thing that we should have accomplished now that we're all done with these problems is we should have finished the table. There's only one spot on the table. And in order to figure out this spot, I need to know how to go forwards. Anyone know how to go forwards, or did you have a different strategy that you used? Gavin D, help me out. Perfect. That's a great strategy. You didn't know how to go forward, so you worked backwards, and you did 25 divided by 20. I'm guessing when you did that, you got 5/4. And as a decimal, you got 1.25. And you can decide, I don't care if you use 5/4 or 1.25. Because there's already decimals in this problem, I'd probably use decimals. But fractions are still friends. So if you wanted to keep it at fractions, you can. So did you actually check it? How do we go forward? It says that we should be multiplying by 1.25. Are we really? You tested it out? It works? Great. So what am I doing here? 1 multiplied by 1.25 gives you 1.25. Voices off, please. I'll just keep waiting. Thank you. Now we need to plot the pairs of values on the grid. So I'm going to try and come down as much as I can and try and graph these points. We do have 0, 0. That one's an easy one for me to graph. 0, 0. The next point that I should have graphed is 20, 25. So over 20 and then up 25. And then over 30, up 37.5. Over 30, here's 30, here's 35. 37.5 would be halfway between. And the other one is 40, 50, and it's already up there. And the last one is hard. I'm actually going to save that one till the end, and you'll see why in just a second. Okay, it doesn't say to do this, but I want you to notice that all of these points form a nice straight line that goes all the way back to the origin. And the reason why I wanted to wait to plot that very last point is because it's a lot easier to figure out where that 1, 1.25 is going to be when there's the line already there. Because here's the 5, and then I have to break that 5 up into 5 pieces. I think that the 1 would be approximately here, right? It's not perfect, but that's about where it's going to be. Okay, what does the point 0, 0 mean in the situation? Who would like to share their answer? Thank you. Jada. Yeah, he hasn't moved at all. And he hasn't moved at all because we haven't even started the time yet, right? So the 0, this first 0 means 0 seconds. And the second 0, remember we're measuring that distance. So that's 0. Is it meters or yards? I already forgot. Meters. Okay. 0 seconds, 0 meters. We can interpret that to mean in 0 seconds, when we're not even timing, then he's not even moving. Makes sense. Here's where it gets to be challenging. How far away from the ticket booth was Tyler after just 1 second? Can we find that point on the graph? Yeah, we can. In fact, we already have, right? What did you come up with, Emma? Good, 1.25 meters away. We actually see that information on our table, don't we? After 1 second, he's 1.25 meters away. Fun fact, this is called the unit rate. Because this is how many meters he went after 1 second. That looks like a unit rate, right? Something per 1. Something per 1, that's our unit rate. And we can see that unit rate here on the graph. In fact, that's kind of important. Let's go ahead and put a star by it. That's our unit rate. That's a big deal. Label the point on the graph that shows this information with its coordinates. So that is going to be the coordinates 1, 1.25. And I put a star there because it's our unit rate. Number 5 says, what is the constant of proportionality for the relationship between time and distance? We had to find that out in order to answer this question. So that's easy to say that the COP, the constant of proportionality, is 1.25. But what does it tell us about Tyler's walk? Can you see that 1.25 in the graph? Sam? Every single second he's moving another 1.25 meters. You know what you just described to me? The unit rate. Because isn't that exactly what we set up here too? And have you heard me say before that the unit rate and the constant proportionality are the same? So we're not surprised, right? That when we ask here for the unit rate and we ask here for the constant proportionality, we're getting the exact same information. And again, where do we see it in the graph? Right here, where the unit rate is, where the x value is 1. Let's write that down. We see it where the x value is 1. Now, are you ready for your challenge question? Yes, you are. Close your eyes again. Envision you're at that amusement park. You're now Tyler. You're walking over to the bumper cars. It takes you 40 seconds to get there. But you love the bumper cars. And you see that line is forming and you don't want to be at the back of that line. So you want to get there in half the time. Do you have to walk faster or slower to get there in half the time? You have to walk faster. Good. Keep that in mind. Open your eyes. So Tyler, or you, want to get to the bumper cars in half the time. How would that graph change? How would the table change? How about that constant of proportionality? Let's take 60 seconds and discuss with your group. How are they going to change? Online learners, pause the video to give yourself that think time. So, Tyler wants to get there in half the time. How is that going to change the graph? Who wants to give it a shot? Trinity, what do you think? Depends on what you mean by everything would be in half. Let's look at the graph. How would it look different? Berkeley. We would multiply the meters by 2. You're kind of right. Because now we have to, in 1 second, instead of going 1.25, we have to go double that amount, right? So that we can get there in half the time. Exactly right. Let me help you out with this visual. Eyes on the screen. Is the bumper cars moving further away from us or getting closer to us? No, they're staying where they are, right? So we still have to go 50 meters. How long did it take us or did it take Tyler to go that 50 meters the first time? 40 seconds. But we want to get there in half that time. So how long should it take us now? 20 seconds. So we still have to go 40 meters, but we have to go there now in 20 seconds. Let me switch colors here. So what is that going to look like now? He goes from here up those 50 meters, away 50 meters, but it only took him 20 seconds. Let's compare that to what Berkeley said. She said that would mean everything would have to be doubled. Is it doubled? Let's see, this took us 25, double that, and 50. Looks like it. This was 1.25, double that, and it's 2.5. Yeah, my graphs are not super duper accurate. 2.5. Very good. So how would the graph change? The graph is steeper. Which also means that that constant of proportionality has to be bigger, has to be, as Berkeley said, double. Because we have to go twice the distance in the same amount of time. Seagulls eat what? This is an interesting problem. I don't know if it's true or not, but it's crazy to think about. 4 seagulls ate 10 pounds of garbage. Assume this information describes a proportional relationship. Plot a point that shows the number of seagulls and the amount of garbage they ate. Then use a straight edge. You guys have rulers in your baskets at your table. Use a straight edge to draw a line through that point and 0, 0 the origin. Make that happen right now. Should take you about 20 seconds if you're on task. We're not going to pause the video. We're just going to keep on going through this. Plot that point that shows 4 seagulls eating 10 pounds of garbage. Time is up. This is what your point should look like. 4 seagulls eating 10 pounds of garbage. Okay, good. You guys caught my mistake. Did I use the right numbers? Did I put them on the graph in the right position? No. The 4 is for the seagulls. So that would be 4 seagulls eating 10 pounds of garbage all the way up here. It is very steep, you're right, because that is a lot of garbage. And the next part it says use a straight edge to draw a line that goes from here all the way back to the origin. And now let's make some connections here. It says plot the point 1, k. But it doesn't tell us what k is. But guess what? It doesn't need to tell us what k is because we can find the 1 here on the x-axis. So I go over to the x-axis 1. How far up am I? Not quite 2, not quite 3. What would you say? Maybe 2.5. Okay. We can say probably 2.5. So this would be 1, 2.5. So what is the value of k? If it says 1, k, and we say it's 1, 2.5, then k is equal to 2.5. What does it tell us about this context? Well, think about that. What does the 1 represent? 1 seagull. What does the 2.5 represent, Emma? The amount of trash. Exactly how much? 2.5 pounds of trash. So how much is 1 seagull eating? That's a lot, right? Like I said, I don't know if this is real, but holy cow, that seems crazy. And this is a really important point again. I'll wait. That's fine. It's such an important point. I'm going to put a star there again. Because what does that point represent? It is the constant proportionality and the unit rate. Yes, they're the same thing. How can we identify this exactly? I'm going to kind of back up just a little bit. Let's put our X here, the number of seagulls, our Y here. Here we have 4 seagulls eating 10 pounds of trash. Do you know how a 4 becomes a 10? No, so we would work backwards and go 10 divided by 4. And 10 divided by 4 is equal to, was our estimate right? Yeah, 10 divided by 4 is 2.5. So we really are going forward in the table by multiplying by 2.5. Good connections. Now it's time to summarize. That was quick. It was a nice, fun lesson. Voices off, though, so that we can summarize. For the relationship represented in this table, y is proportional to x. So we can see in the table that 5/4 is the constant of proportionality because it's the y value when x is 1. Y value when x is 1. But even more than it being the constant proportionality, it is also the unit rate. We can see it's a constant proportionality because how does a 1 change to a 5/4? Obviously by multiplying by 5/4. So unit rate and constant of proportionality. And once I know the constant of proportionality, I also can write the equation, which it shows here. The equation is y equals 5/4 x, and it represents this relationship. But we can also see the relationship here in the graph. What if I made the x value represent how many feet the snail crawls? And, oh, no, I'm sorry. Let me back up. What if I made the y value represent the distance in feet that a snail crawls in x represents the minutes? Then what does this point 4,5 tell us? Well, the 4 would be the minutes, and the 5 would be the feet. Or in other words, in 5 feet, if the snail goes 5 feet, it will take 4 minutes. What if I change the situation though, and instead of a snail going 5 feet in 4 minutes, what if the y instead represented cups of yogurt and the x represents teaspoons of cinnamon? Then the point 4,5 represents 4 teaspoons of cinnamon for every 5 cups of yogurt. All we're doing here is we're just interpreting these graphs. We're taking whatever the points are and giving them meaning according to the situation. We can also find the constant of proportionality by looking at the graph because 5/4 is the y-coordinate of the point on the graph where the x-coordinate is 1. Remember, that also means that's the unit rate. And so depending on what that situation is that we're looking at, it could mean that the snail is traveling 5/4 feet per minute, or notice that 5/4 is the same as 1 1/4. Or if the situation is dealing with the yogurt and cinnamon, that's 1 1/4 cups of yogurt for every teaspoon of cinnamon. These are just unit rates for the situation. So, in general, when y is proportional to x, the corresponding constant of proportionality, also the unit rate, is the y value when the x value is equal to 1. So look for that x value equal to 1. That's your constant of proportionality or your unit rate. Let's take a look at our cool down now. Water runs from a hose into a bucket at a steady rate. The amount of water in the bucket for the time it is being filled is shown here in this graph. The point 12,5 is on the graph. What do those coordinates tell you about the water in the bucket? Then, how many gallons of water were in the bucket after 1 second? Label that point on the graph that shows that information. Pause the video and give yourself a chance to work through this. Okay, so what we should have seen is the x value, the x-axis, is measuring time in seconds. So when I see this point here with the coordinates 12, comma 5, I know that that 12 is measuring time in seconds, and the 5 is measuring water in gallons. So specifically, that would be 12 seconds and 5 gallons. Or maybe another better way of saying that would be 5 gallons in 12 seconds. How many gallons of water were in the bucket after 1 second? Well, again, we can see that here on our x-axis. Here's our x value of 1. How many gallons of water were in there? This one is a little bit hard. It looks like it's half. But if we take the time to actually set up a little miniature table where we have our x value of 12 and our y value of 5, we would ask the question, how does a 12 become a 5? I don't know. So we would work backwards and we would go 5 divided by 12, and 5 divided by 12 is equal to, don't worry about the decimal approximation, just keep it that fraction, and 5 divided by 12 is the fraction 5/12. So that tells us how we are going forwards. We're going forwards by multiplying by 5/12. And the reason that's important, the reason we are accurate and we find that constant of proportionality is because now when I have the x value of 1, which we're seeing right here, we know that to go forward across that table, we would multiply by 5/12. And 1 times 5/12 is 5/12. So it looked like it was half. It's actually just a little bit less, but now we can label those coordinates 1 comma 5/12. We've labeled it here on the graph, and again, it's important. It's our unit rate. It shows our constant proportionality, so I'm going to go ahead and mark it with the star. That's it for today's lesson. Your homework is the Lesson 11 practice problems. Please don't forget, for you online learners, to enter your cool down into Canvas. Thanks for watching. We will see you next time.